Previously, I asked if you could find the gradient of the tangent to a curve, and we discovered differentiation was the solution. Here's another classic problem. Can you find the exact area underneath a curve such as x squared? Archimedes solved this problem for parabolas. He used a method called quadrature of the parabola. But just as with tangents, it wasn't a generalizable solution. He could find areas under parabolas, but give him a different kind of curve, and he needed a different method. So again, just as with differentiation, we're looking for a method that generalizes to any type of function. Again, it wasn't until Newton and Leibniz came along about 2,000 years later that a general solution was discovered. So we want to fast forward to the 17th century to find out how we're going to find this area. The first thing we can recognize is that we can approximate the area using rectangles. So this could be an underestimate or an overestimate. For example, if I draw the rectangles underneath the curve, then that's going to give me an underestimate. We could also find an overestimate by drawing the rectangles above the curve, like so. Let's also recognize that making the intervals smaller gives us a better approximation of the area. So we can see here that if we make the rectangles skinnier, we're covering up more of that area. So that's going to give us a better approximation. Let's remember this point for later. Let's keep that in the back of our minds for now. So this is the method we're going to begin with. And let's start with a curve like x squared. So we're going to look for the area up to 6 on the x-axis. And we're going to divide this area up into 6 partitions. So we're going to get 6 rectangles with widths of 1. So to find the area of those rectangles, we just want to sum up their areas. So width times height plus width times height and so on. Let's firstly calculate the overestimate. So we're going to be looking at these rectangles above the curve, starting with this one down here. This goes from 0 to 1. It has a height of f of 1, right? Because where this rectangle intersects the curve is its height. And for the second rectangle, its height is going to be f of 2. Again, it has a width of 1. The third rectangle for the overestimate, its height will be f of 3, and the same width again. F of 4 for the height of the fourth, f of 5 for the height of the fifth, and f of 6 for the height of the sixth rectangle. So we get this sum. We can multiply them all by 1 because they all have a constant width. Okay, we can figure out this. This has a value because we know the function is x squared. So we're just going to square those inputs. So f of 1 is 1 squared. F of 2 is 2 squared. So we get 1 plus 4 plus 9 plus 16 plus 25 plus 36, which gives us an overestimate of 91. Very nice. Let's look at the underestimate. An important point here is that we do include a rectangle from 0 to 1. Even though it has a height of 0, we're still pretending that it's there because sometimes this curve might not start at 0. In other words, it might be above the x-axis, and in which case we do have a rectangle as the being under the curve. So we pretend there's a rectangle here with a height of 0. Then the second rectangle for the underestimate is going to have a height of f of 1 and a width of 1. The third rectangle has a height of f of 2, and so on. So we get this sum for the underestimate, starting at f of 0 up to f of 5. This, again, we can work out will be 0 plus 1 squared plus 2 squared, and so on up to 5 squared, which gives us a total of 55. Again, very nice. We have an underestimate and an overestimate, so that area must be between those two numbers somewhere. Must be between 55 and 91. But we want an exact area. We don't just want some range of values, we want an exact area. So how are we going to do this? Well, we need to start generalizing. So we can call this upper limit of the area B. Instead of 6, let's say B, and let's divide it into n partitions instead of 6 partitions. Okay, so now we have a different width. How can we express this width? If the total width of the area is B, and we divide it by n, then each width of each rectangle will be B divided by n. And if we talk about the overestimate, the heights of the rectangles will be f of x1 plus f of x2 plus f of x3, whatever those values are. So we can express this overestimate in a more general way. We can say it's the width of the rectangles b divided by n multiplied by all of the heights. So we have this general expression for a range from 0 to b, and we're going to write it like this. We're going to use this sum symbol. This strange capital E kind of looking symbol means the sum of. So all this means here is we're summing f of x from 1 to n, just as we did here, but instead of having to write this whole list out, we can just write this symbol. So it's just a shorthand way of writing a large sum of things. Let's have a look at our diagram again. And we said we were looking at the curve of x squared. Now we're just going to look at a general curve, f of x, and we observed the width of those rectangles would be b over n if we looked at a domain from 0 to b. So let's have a look at a point on this curve, one of the heights of the rectangles, and let's say this was the fourth interval along. So we go from 1, 2, 3, 4 up to the fourth height of the fourth rectangle. What would this point on the x-axis be? If we have gone along the x-axis 4 partitions and each width is b over n, then that x-coordinate will be 4 times b over n. And that height will be f of x, in other words, f of 4 times b over n. In general, if we pick another point, let's pretend we don't know where that is, some other height of another rectangle, we could say its x-coordinate will be k times b over n. So whatever position it has in those partitions, that will be k, and its height will be f of k times b over n. So notice how we're trying to generalize as much as possible. This is actually going to help us solve this problem. So we can say if we let xi equal k times b over n, xi was just the x-coordinates of our partitions, then the heights of the rectangles could be defined as f of k times b over n. That's just what I said here, where k is the number of partitions up to that point. So for the area from 0 to b, we get this sum. We could write it slightly differently. We could say it's b over n times the sum of f of k b over n. Okay? So again, all I'm saying here is it's the width of the partitions multiplied by their heights, which we've redefined as f of k times b over n. Okay, now we have this general expression. Let's go back to our specific example of x squared and see what we can do with that. So for f of x equal to x squared, we have that the overestimate of the area is this sum, this expression we've just found. But let's have a look at what happens to f of k times b over n. Well, if f of x is x squared, we square that input. So we're going to have b over n, the width of the intervals, multiplied by the heights squared. Or those x-coordinates squared, sorry. Okay, so we're going to have to evaluate this in a moment. Let's have a look at the underestimate. This is an important point as well. Here, instead of getting k times b over n all squared, we get k take 1 times b over n all squared. Remember, on that first example we looked at, we subtracted 1 from the input of each height, and that's all we're doing here. We're saying instead of k is k take 1 times b over n all squared. Okay, so we have these two sums for the overestimate and the underestimate. What can we do with these? Well, let's have a look at them specifically. So this was the sum for the overestimate for f of x equal to x squared. We can square that term in the brackets and factor out a b squared over n squared and write it like this: b cubed over n cubed multiplied by the sum of k squared. There's actually a formula for this. If you sum all of the square numbers up to n, this is equal to n times n plus 1 times 2n plus 1 over 6. This is a well-known kind of result of adding up the squares of the natural numbers. So we're going to substitute this formula in for the sum of k squared from 1 to n. Okay? So we get this result, b cubed over n cubed multiplied by n times n plus 1 times 2n plus 1 over 6. Okay, right now you're thinking, what the heck does this have to do with areas? It will all make sense in a moment, trust me. Let's keep looking at the underestimate. Here we had this sum for the underestimate. We can do the same thing. we can factor out the b cubed over n cubed, and we have the sum of k take 1 all squared, which we can use basically the same formula. It looks a little bit different, but it's basically the same thing. We get k take 1 all squared equal to n take 1 times n times 2n take 1 over 6. Okay, so we have these two expressions for the overestimate and underestimate. And now I want to ask the question, what happens when n gets really large? Okay, remember that n represents the number of partitions we're dividing the area into. And we said, as we increase the number of partitions, the estimates get closer to the real area. So let's have a look at these expressions as n gets really large. What's going to happen? For large n, having a look at n times n plus 1 times 2n plus 1 over 6, this is actually approximately equal to the underestimate. Why is this the case? Well, imagine n is something like a trillion. And we multiply, instead of multiplying by a trillion, we multiply by a trillion plus 1. That plus 1 doesn't make much of a difference, right? So we say as n is getting really large, we can ignore these plus 1s. So in the numerator here, we just get n times 2n, which is 2n cubed over 6, which simplifies to n cubed over 3. The same for this expression here. If we're multiplying by some really large n, the subtract 1 doesn't matter. We can ignore it. So in the numerator here, we just get n times 2n, which again simplifies to n cubed over 3. Okay, so for both the overestimate and underestimate, we are getting a result of b cubed over 3. What does this mean for the area we're looking for? What did we find? Well, we found the overestimate was either greater than or equal to b cubed over 3. Remember, b was our upper value of our area. The underestimate was less than or equal to b cubed over 3. And we can see that as we increase the number of partitions, as we increase the number of rectangles we're splitting that area into, the estimated areas converge to b cubed over 3. When the over and underestimates converge in this way, we say we can integrate the function. Okay, so we had these two sums, and what we were really doing was taking a limit. So these two expressions you might see representing integration. So you're either looking for the limit as the width of the rectangles decreases to 0, or the limit as the number of partitions increases to infinity. And when we integrate, we write it in this way. So this symbol here is like a large S. It's similar to these sum symbols, but it represents the fact that we are taking the sum of these rectangles as the number of rectangles approaches infinity, or the width of those rectangles approaches 0. So this symbol is kind of saying we're taking a limit. We're finding these sums at the limits. So this symbol is our integration symbol. So this equation here says we're integrating x squared from 0 to b. We're finding the area under x squared from 0 to b with respect to x, and we get a result of b cubed over 3. In other words, the area under the graph of x squared from 0 to b is b cubed over 3. This is what we call integration. One interpretation is we're finding the area under a curve. So if we want an answer to our original problem, for example, if we're looking at the area from 0 to 6, we'd plug in 6 here. 6 cubed is 216 divided by 3 is 72. So we get an exact area under x squared from 0 to 6 of 72 units squared. Okay, so why do we care about areas under graphs, areas under curves? Well, apart from it being an interesting, kind of brain teaser by itself, we use areas under curves to represent many things. They could be distance. If we graphed speed, the area under a speed time graph is distance. You can use integration to find volume. If you graph acceleration, the area under the acceleration graph is speed. I was reading about something called the modulus of toughness. You can use integration to find the toughness of a material, which is how much energy it can absorb before it fractures. You can use integration to find weight, materials needed for construction, and it's used in many areas of mechanics and physics. Some of you might be asking, it's great we can find these areas, but do we have to, draw these rectangles and find the areas of the rectangles every time we want to find the area under a curve? Luckily, we don't. In the following videos, we are going to discover an incredible relationship between integration and differentiation, and it's going to make our lives much easier going forward. So stick around for that. If you found this video helpful, please leave a like. Subscribe if you want to see more content, and I'll see you in the next one. Bye for now.